Good morning, everyone. Today is April the 6th. Welcome to the IME 470 class. First, let me share my screen. Okay, so can you see my screen now? Can everyone see my screen? Showing about the slides and the Excel file. I'm not sure whether, let me see. Stop share. Give me 1 second. Let me reshare it. Looks there's something wrong. Okay, now it's correct. Okay, here we go. So in the last lecture, we discussed about Dijkstra's algorithm, and we showed the steps. In the very beginning of this class, I do need to review this algorithm, which is too important. So in the very first iteration, let me establish this one. Nodes fj, and also I have the path. Okay, let's make the path a bit bigger and make everything to be in the middle. So I have S1, 2, 3, 4, 5, 6, and the T, total of 8 nodes. And let me make something, make it a bit more beautiful. And let's see. Okay. In the initialization, which is iteration number 0, what do we have? We have S as star, and all others are infinity. We put everything here. Okay, and F star is clearly Fs is clearly fixed because it is with itself. And here the distance is, the distance should be S. Okay, so this is my initialization, and I use a bold font to indicate this is the most recent added node. Okay, now let's have a look what's gonna happen in iteration 1. In iteration 1, what we're gonna have is that, well, since node S is the most recent added node, I'm gonna see from S, I can go to which nodes? I can go to 1, go to 5, and go to 6, and hence I need to update 1, 5, and 6. Go to 1, previously infinity, now it is from S to 1 directly, which is 9, so the cost is 9. So here becomes S1. To node 5, similar, I have 11. So I have the shortest path as, S to 5 directly. To node 6, it is 17 from here to here. And then my path is S6. Let me make the annotate back so that you can see more clear. Here we go. Okay, so this is a temporary table of, let's say, temporary distance of iteration 1. Okay, now what we're gonna do, first we're gonna, update the distance. And the second is what? Is to fix a temporary distance. Among all these numbers, among all temporary distances, which one is the smallest number? This one, right? Because this one is already fixed with the star. Okay, so we're gonna fix this one. Again, a star means it's permanent, it's fixed. And a bold star means it's the most recent added node, or the most recent fixed node. Okay, now we're gonna go to iteration number 2. Again, step number 1, which is to update the out neighbors of the most recent added or most recent fixed node. So the most recent fixed node is node 1. From node 1, which one can I get to? Node 2. Let's see. Okay, so node 2 is infinity. So the distance from S to 2 is equals the distance from S to 1 first, and then from 1 to 2, which equals 9 plus 24 equals 33. And the route becomes S to 1 to 2. Okay, and that's the only one that from 1 I can go to. Now have a look at here. Among all these 3 temporary distance, which one is the smallest one? Very clear, the one with node number 5. So I'm gonna fix it and bold it because it's the most recent one, right? And let me see. And then the next step, what we're gonna do, here's iteration number 2. What we're gonna do is the same, to update the temporary distance of node number, number 5. So from 5, I can go to 2, go to 4, or go to 6. Let's see. First, from 5 to go to 2. The current one is 33. From S to 5 is 11. 11 plus from 5 to 2, which is 18. 11 plus 18 is 29. 29 is less than 33. So that I'm going to update it to be 29. And hence here, I just copy and paste. I'm going to go from S to 5 to 2. And the second one is to 4. 4 currently still infinitive. So I have S to 5 is 11. 11 to 4 is 30. So it is 31. And similar, I have S to 5 to 4. And the last one is 16. Sorry, and 6. So from S to 5 is 11. 5 to 6 is 5. So it is 11 plus 5 equals to 16. 16 is smaller than 17. So yes, we need to update. And correspondingly, the route becomes from S to 5, from S to 5, and then 5 to 6. Okay. Now we again have updated all the out neighbors table of node number 5. Now we need to go to step number 2, which is to fix a node among all the temporary nodes. Currently, I have 29, 41, and 16. So which one is the smallest one? Very clear, 16. So I'm gonna fix 16 and continue. Okay, the good point is that I can use Excel. I'm really excited about this. I don't need to, you know, like on the whiteboard, I have to copy and paste manually, which is really slow. Okay, now let's have a look at node number 6. From 6, I can go to 4 and T. Let's have a look at 4 first. The shortest path, the shortest distance from S to 6 is currently fixed to be 16. From 6 to 4, it is 20, cost 20. So 20 plus 16 is 36, which is smaller than the current shortest distance, which is 41. So I'm gonna update 16, and then here I'm copy and paste from S to 6 first, and then from 6 to 4. So the route is updated, the path is updated to be S to 5 to 6 to 4. Do the same for T. T is currently infinity, great. So I have 16 plus 44, which is 60. And do the same. S to 5 to 6 to T. Okay, very good. Now, again, go to step number 2 to fix the node. Currently, I have 29, 30, 36, and 60, right? So which one is the smallest one? Very clear, 29. So I'm gonna fix 29. Okay, and then 29 means node number 2, and then continue. Let's continue. Here we go. Iteration number 5. Okay. From node number 2, which one can I go to? I can get to 4. I can get to T, only 2, right? Yes, only 2. Okay, let's have a look. From S to go to 2, it's fixed to be S5 to the cost or the distance is 29. But from 2 to 4, it costs only 2. So 29 plus 2 equals to 31. 31 is smaller than 36, which is the current smallest distance. So I'm gonna update 31. And correspondingly, I'm gonna change this one to be S to 2 to 4. And then the next one is what is T. The next one is T. For the T part, it is currently it is 29 because it's the 2 is the most recent added node. So 29 plus 19. 19 is the cost from 2 to T equals to 48, which is less than 60, the current shortest distance. So I'm gonna update. And similar, what I'm gonna do is copy and paste this one. So I'm gonna change the current shortest path to be S to 5 to 2. Okay. Now again, among all these temporary nodes, where a temporary distance we're gonna update. Currently, I only have these 2, right? So clearly, 31 is the smallest one. So I'm gonna choose node 4. fixed node number 4. Then let's do, because current time, what is that? Because here I only have one case, so for sure I'm gonna be successful. Means I'm gonna done after here. So, wait, why there's still a, I realized I made a mistake. Give me 1 second. Give me 1 second. Here I think I fixed node number 4, I updated. Wait 1 minute, what did I do here? I fixed node number 4, right? And sorry guys. Here I think I have a mistake here. Let me see. Okay. Yes. Here I have 2 things. It's not. I cannot claim that I will be done, because because of what? Because here is I fixed node number 4, but no, here's another infinity number 3 here. I didn't see a 3 just now. Okay. Now let's continue here. From node 4, I can go to 2 nodes, which are node 3 and node T. So I'll have a look at node 3, it is still infinity. To 4, it's 31. 31 plus 11 equals to 42. And correspondingly, I can copy and paste and get the temporary shortest path from 4 to 3. And now let's go to T, let's have a look. To 4, the shortest distance is 31. 31 plus 16 equals to 47, which is smaller than 48. So I'm going to update. And similarly, I'm going to update this one here. Okay. And then in this case, I have the table like this. And again, I have 2 temporary nodes, 42 versus 44, sorry, 47. So I'm going to fix 42 because it is the smallest temporary distance. So I'm gonna fix 42. Oops. And then continue. Let's go to iteration number 7. Yes, this time I'm gonna finish because there's only 1 temporary node, which is T itself. Okay. And then because I fixed 42 node number 3 to see here, from 3 I can go to node 2 and the node T. However, have a look at here. Node 2 is already fixed. See it? Again, once it's fixed, it's permanently fixed. I will never try to update its distance. So I'm not gonna do anything to node number 2. Node T, you see, it's not fixed. Let's have a look. So from 3, from S to 3, currently not currently, actually it's permanent. The shortest distance is 42 with the route S to 5 to 2 to 4 to 3. Then from 3 to T, it's gonna cost me 6. So 42 plus 6 equals to 48. However, 48 is greater than the current shortest distance, which is 47. So I'm not gonna do anything. Now, step number 2 again, I'm gonna fix a node. Here you have only 1 choice, which is 47. So of course, you're gonna fix this 47. And then mark this one as the most recent added node. Okay, now since T is already fixed, so I'm done. So finally, my shortest path would be S to 5 to 2 to 4 to T. And the shortest distance is 47. It should be correct. You know, up here. And yes, S to 5 to 2 to 4 to T. And the shortest distance is 47. Okay, see it? Any questions? Any questions?
Program this into like Excel to do this.
Yes, here you can definitely use Excel to do this. The reason that I use Excel here is to make you guys see it very clear. In the real cases, nobody's gonna really use Excel because this graph is super small, a super baby graph. And in the real cases, you may have thousands, even hundreds of thousands of nodes. In this case, they're gonna code it, because you can clearly see it's very easy to code. See it? The outside is what? A while loop, which is to see whether node T is fixed. And then inside the while loop, you're gonna see what? You're gonna have a for loop, which is for all the out neighbors, you're gonna do the update using this formula. You know what I mean? So it's extremely simple. Of course, when I'm showing this one, I'm teaching it, I use Excel to show step by step everything very clear. in your homework, you can, you can use Excel or you can do whatever. It's not a big deal. As long as, the purpose is to let you clearly understand what does the algorithm do step by step. Any other questions?
Yeah, isn't there another shorter distance though?
Is there another shortest distance?
Yeah,
don't
so if you
think
go
so.
S to 5 to 2 to 3 to 3. So if you go S to 5 to 2 to 4 to T, 2 to 4 to T is 18.
Oh, it's slow. Sorry. Slow. What did you say again? Could you please repeat the path again? S to what?
S to 5 to 2 to 3 to T.
No, you cannot. 2 cannot go to 3. See it? That's one way.
Oh, yep, I see it. I see.
Yes.
Okay.
And I think, wait, this is a good question. If suppose all the lengths they're undirected. In other words, all these arrows are double arrows. So then I guess the one you said is even smaller. Yes, look at this. If in this case I can go to 2 to 3, 3 to T, right? So this costs you 12. 12 plus 18 is 30, plus 11 is 41. If that's the case, then the path that you propose is shorter than the path that we currently have. But unfortunately, here you cannot go this way. And this is a very good question because think about this. Suppose I can go this direction, then what's going to happen? Because in this case, when you're updating node number 2, you will directly consider node number 3. See it? You want, for example, let's get to the case out. Okay, here where I fixed the 2. I fixed the 2 here, 29. No, but if that case, the option is 4. Here your 4 is going to be changed as well. A lot of things are going to be changed. And I guarantee you, if you use the Dijkstra's algorithm to solve it, you're going to get the correct answer again. The only difference here is that you're going to have more out neighbors, see it? Because currently, 3's out neighbor is only, let me see this. 4's out neighbor, let's see, is only 3 and a T. But if you let this one be possible, then 4 can go to 2 as well, right? Similar, 2's out neighbors are only 4 and a T. If you make this become a double arrow, then 2 can go to 3 as well. So in this case, yes, the iterations will be updated, and the answer very clearly is going to be changed. Very good question. I think in your homework, I have a smaller or bigger graph I've got, but very similar that many of them has bidirections. In other words, many of the this kind of arrows are undirected. If these arrows are undirected, then you're going to have a lot of fun because while you have more choices of out neighbors, and you still the same, you just perform the Dijkstra's algorithm, and it should give you the same answer. The correct answer, not the same answer. Answers will be different. Any other questions? No? Okay, then let me ask you a question. Before we formally summarize this algorithm, where's my question? I think the last page. Here you go. What if I change this W43 from 11 to 19? So currently W43 is 11, right? But what if I change this number to be 19? You might say, hey, what is the difference? Looks the same. We're still gonna, run the Dijkstra's algorithm, right? Absolutely correct. But something would be changed. Let's first have a look at the iteration where we fix 4, because only here from 4 to 3 is changed. So I only need to check the iteration where I fix 4. Actually, the iteration after the step that I fix 4. Let's see where I fix 4. Here we go. In iteration number 5, we fixed the 4. See it? Okay. All the previous cases will be the same. Let's copy and paste iteration number 6 to see will there be any difference? Oops, what did I do? Copy and paste. Come on, computer, do it. Copy and paste. Okay, let's make it a little bit bigger. So here, let me ask, what if W43 equals to 19? Okay, so if W43 equals to 19, what do you have here? So this is, let me see, no, I should have copy and paste here and make the new iteration number 6. Okay, so this is still the last table of iteration number 5, in which my node number 4 is the most recent fixed node, right? Okay, so let's do repeated. From 4, I can go where? I can go to 3 and t. So let's have a look at the 4 to 3 here. Currently, 3 is still infinity. Okay, so to go to node number 4 is 31. And then here, 43, we said it is 19. So 41 plus 19 is what? As, really? 31, sorry. 31 plus 19, it is 50. And your route is going to be the same, 4 to this, and then to 3. Okay, now we're going to update t. Similar, the current t is 48, and from 4 to t, it's going to cost us 31 plus 16 equal to 47. And then I'm going to change the route as well, update it to be this. Okay, very good. Now let's do the next iteration. In your next iteration, what will you do? You're gonna, oh, okay, not next iteration. Here I'm gonna fix. Here you go. The difference is right here. So currently I have 2 temporary neighbors, temporary distances, which are 50 and 47. Then which one would you fix? You're gonna fix this one, right? Because this one's smaller. In other words, you're gonna have this result. Here we go. Everyone, did you see a difference? I no longer need iteration number 7. Why? Because I'm done. Who cares? This 3, you say it's not fixed or not. I mean, of course, in this specific example, in the next iteration, I'm going to fix 3 because, you know, that is the only choice. But even if, suppose I have a node number 7, suppose, okay? Suppose both 3 and 7 or whatever, how many nodes that you have, none of them are fixed. It doesn't matter. Why? Because my t is fixed. Your target is t, from S to t. You know what I mean? So in this case, as long as your t is fixed, you are done. Mission accomplished. That's it. Okay. So yes, this question tells you this point. Optimality test. As long as t is fixed, I'm done. Okay. Now let's have a summarization of the Dijkstra's algorithm. After running this example, I think this summarization makes more sense for most of you guys. First of all, I'm gonna do initialization, which is, okay, let me still use this way because it's gonna be more clear. In the initialization step, what I'm gonna do is that I'm gonna fix node number S, and I'm gonna put the route or the shortest path from S to S. Of course, it's itself. So it's the path is S, and all others become infinity. And here you can write empty set, or like me, I'm lazy. I just leave it to empty. So this is my initialization. So in each iteration, I'm gonna do what? I'm gonna do 2 steps. Step number 1 is to update out neighbor's temporary distance for the most recent added node or the most recent fixed node. So here, for example, my most recent fixed node is node number S. So that I'm gonna check who are S out neighbor. Out neighbor means from S, I can go to which node? And I can go to node 1, 5, and 6. So I'm gonna update the temporary shortest distance of node 1, 5, and 6. How to update? You're gonna update by this formula, this recursive formula, which is to go to node number J, I'm gonna find the, let me see. I'm gonna compare the distance of Fj, which is the previous shortest distance, versus this most recent added node, plus from this node I star to J. Okay, where this J is in this NF star minus Ni star minus fixed node. This means what? This means J is the out neighbor of I star, where I star is the most recent added node, minus fixed star. Remember, there's an example here. when I'm updating node 3. Remember here, from 3, I have two out neighbors, node number 2 and the node t, right? But I will not update node 2. Why? Because 2 is already fixed. That's the reason why you need to add minus this node, minus this fs, because once a node is fixed, fs means the set of fixed nodes, index set of fixed nodes. If a node, out neighbor of my I star is already fixed, then I will never try to update it again. So I'm going to only update the out neighbors of the most recent added node, which is temporary. Okay, so you're going to update your out neighbor j to be the minimum of the previous shortest distance versus the new distance. The new distance is composed of from S to I star first, which can be found directly by Fi star, again, because it's fixed. So I will never need to update it, it's permanent. Plus from I star to J. So this shows you the cost or the new distance. And which one is smaller? Suppose the previous one is smaller, great, do nothing. You don't do nothing means you don't need to update the shortest path, Pj. Otherwise, if the new distance is smaller, then yes, you do need to update the Pj by the path to I star first. Then after it, from this one to go to J. For example, let's randomly find one. For example, let me find one, let's say here. Let me find one bigger. For example, which one is? Let's find something like this way. Here, node 6. Node 6 is from 5 to 6, right? So you're gonna compare the previous distance is 17, and the new distance, where it is? The new distance is from S to 5, which is 11. 11 plus 5, which is 16. So 16 is smaller than 17. Then yes, I need to update the path to 6. So how to update the path to 6? You're going to go to 5 first and copy and paste. What is the shortest path from S to 5? It is directly S to 5. Then use this one and add a 6. So S to 5 to 6. Here we go. Okay. In general, it is you're going to update it by the shortest path from S to I star, which is recorded by Pi star, and then followed by this J. And this is the method how you can update out neighbors' temporary distances of the most recent fixed node. Next step, you're going to fix a node. That is much easier, which is if you see a node as temporary, then you're going to consider all these temporary nodes, the distance of all these temporary nodes, to check which one is the smallest one. We're going to always, among all temporary nodes, in other words, nodes that are not in the set Fn, we're going to fix the node with the minimum temporary distance. Or equivalently, we can say, put the node with the minimum temporary distance to Fn to fix. And what if there's a tie? If there's a tie, it doesn't matter. You can randomly choose one. Or let's say to make your life easier, you can always choose, for example, the index, the smallest index, if there's a tie, or the biggest index. As long as you keep the same rule, it doesn't matter. And finally, optimality test. You're going to check whether T is fixed. If T is fixed, you're done. It doesn't matter whether all nodes are fixed or not. As long as T is fixed, you're done. If T is not fixed, go to step number 1 and repeat again. So very clear through all these steps. I'm doing only 2 things, mainly only 2 things. You know, this is too simple. It's not counted. First, updating out neighbors' temporary nodes for the most recent added or the most recent fixed node. Then fix the node by choosing the minimum shortest distance, temporary shortest distance, and then updating its out neighbors' temporary distances again, and then fix a new node, and then repeat until T is fixed, and then I'm done. Any questions? Again, after the class, please do this example, you know, because I do have all the steps here, or you can watch the video here, do the steps one by yourself, and then you're gonna understand this algorithm and these steps are very clear. Any questions? No? Okay. And the second question, the second problem that I want to introduce about the Dijkstra, about the dynamic programming in addition to Dijkstra's algorithm, is the so-called knapsack problem, or the UKP, unbounded knapsack problem. So the definition of knapsack problem is in this way. I have n candidate types of items to put into a knapsack. The knapsack has a capacity, weight capacity, capital W, the big W. And each type of items has a value, and also has some, give me 1 second, has unlimited supply. So you can have infinitively large number of item I, any I. And one copy of item I has a cost, have a weight, Wi, and a value, Vi. Clearly, both of them are greater than 0. And the number of copies of each item must be an integer. I want to maximize the value included in the knapsack. So this is a knapsack problem. Why it's called unbounded knapsack problem? Because each type of the items has unlimited supply. That means you don't have any upper bound for the supply. However, if we do have a limit, for example, currently my xi can be any non-negative integers. But if I limit it to be from 0 to 1 to mi, in other words, the supply of item I is at most mi, then the problem becomes a bounded knapsack problem. Okay, let's have a look how to formulate it. First of all, I want to maximize the value, right? So I'm gonna first denote variable xi to be the number of copies of item I. Be careful here. The number of copy of each item must be an integer. This tells me what? This tells me my xi must be an integer. And also because the supply is unbounded, so that xi can be 0 or any positive integers. And after defining the variable in this way, the objective value, the objective function is very easy to be defined, because the value of one copy of item I is Vi. So totally, how many copies of item I do you have? You have xi copies of item I. Now you're gonna sum of all the values, all the items from item I equal to 1 to n. So this is your total value, which is your objective function. Now have a look at the constraint. The constraint says that a knapsack has a weight capacity, which is W, capital W. This capital W is given. Okay, now the thing is with this capital W, what is your highest value? What is the highest value can you put into this knapsack? So how to formulate the value here, the weight here? So the weight here is again similar. What is the weight for item I? One copy. It is Wi, we know it. Now, totally how many copies do you have? You have xi copies, right? So the total weight of item I is what? Is Wi xi. And totally you have n items. So you just sum all of this. And this is finally the model for the knapsack problem. This is very simple actually. Any questions here? The MILP model, mixed integer linear model, is here. The reason I call it a mixed integer linear is because first of all, it is integer. Second, you can see with respect to x, both the objective function and the only constraint here, both of them are linear. So it is called mixed integer linear program. Any questions? No? Okay. Indeed, this model is very simple. Now let's have a look at one example. So suppose the knapsack has a total capacity of 25 pounds, and the weight, and I consider 4 items: apple, banana, pears, and oranges. Okay. Now suppose the weight of 1 apple, banana, pear, and orange are, seriously, 2 pounds. Okay, that's really a big apple. 2 pounds apple, 0.8 pound for a banana. I don't believe it's so big. Okay, 1.5 pounds for a pear and 0.5 pound for an orange. Yes, the orange is normal, I think, respectively. And then consider the value of 1 copy of apple, banana, pear, and orange to be 10, 3, 8, 2. Okay, apple has a very large value. For example, consider you are gonna go to, let's say, desert area. You need water, so that, you know, like apple and a pear, they contain a lot of water. They're gonna be very, very valuable. Just a joke. And now I will have unlimited supply on these fruits. The question is how to arrange them to maximize the value in my knapsack, because my total weight is only 25. So in this case, you can formulate it in terms of value. You get the objective function, which is 10x1 plus 3x2 plus 8x3 plus 2x4. In terms of the weight capacity, you have 2x1 plus 2.8x2 plus 0.5x3 plus 0.5x4 is less than or equal to 25. And of course, finally, all x's are non-negative integers. Okay, so this is the knapsack problem, UKP integer pro MILP formulation for this knapsack problem. Any questions here? No? Okay. And this problem, first of all, I need to make all weights to be integers. Suppose the weights are, there's a one weight, for example, here, it is not an integer. We're gonna multiply by, you know, we're gonna make them all integers by a multiplier. For example, in this case, we can multiply 2 on both sides of the inequality, so that it becomes 4x1 plus 3x2 plus 8x3 plus 2x4 less than or equals to 12, right? So in this case, you can see all the weights are integers. What I mean is this constraint, not the objective value. Be careful here, the objective function, if there's a non-integer here, it's acceptable, no problem. Later, you're gonna see why. But in terms of the weight here, all of these, for example, 0.8, 0.5, 0.5, they're not allowed. All of these must be integers, okay? By the way, so let me see how to make them to the integers. Oops, here you can only let's say multiply 10 here, both sides, right? Can you multiply something smaller? No way, because you're gonna get an 8 and a 5. 8 and a 5, you have no choice. Okay. And now we assume that all the weights, the coefficient of the weight here are integers. If that is the case, immediately I can run the dynamic programming. Why? Because consider this. Suppose you have a weight W. Okay, be careful. I realize I could have some notation confusion. This W is not related with this W. Okay, so I will change this W to be, for example, C. Otherwise, I mean, you may get a bit confused. This WI is just a fixed constant, okay? It's a constant indicating the weight of one copy of item I. But this W here, what I mean is really a variable. This variable is the variable to, finally, we want to find for small w equals to the capital W. Because Fw represents the maximum value at the knapsack weight equals to small w here. So how to reach to this W? Here's the problem. In other words, how to reach to the knapsack weight equals to this W. Be careful here, because the weight, each of item weight I is Wi. So actually, to reach this W, you only need to check this, W minus Wi. Let me draw a line here. For example, consider this. Your W1 equals to 4, W2 equals to 3, W3 equals to 8, W4 equals to 2. right? Suppose my W here equals to 10. Now, let me ask you, how can you reach to weight equals to 10? This tells you that in order to get to 10, I can either add one item at X4 so that I can go from F8 to go to F10 because the weight here of item 4 is 2. Or I can go from item 3 by adding 1 unit of item 3 so that I can go from F2 plus 8 and then I go to F10. Or I can go from item number 2, which is from item 7, from F7, 7 plus 3 equals to 10, and go to number F10. Or I can go from item 1, which is from F6 to F10. So I do have 4 options. This tells you that if I have already had all the W, the previous W, which is smaller than the current W, then this shows you what? This shows you from that node, the previous W value, what is the maximum value. Okay, then use this maximum value plus the value that you added, which is the value I here. This would be what? This is gonna be the solution from the value I, where Wi is smaller than or equal to W, to the current W. And then you just compare all of them, you're gonna get what? You're gonna get the new FW here. I know this might be a bit abstract, no worry. We're gonna see an example very, very soon. And similar, I use P to indicate the optimal solution. And you can see the notation here, FW and PW are exactly the same as the notation here in the shortest path, because basically they are the same problem. There's no difference at all. Okay, so this is also FJ and PJ, and this is FW and P and PW. Here we go. What we're gonna do here is that we're gonna start from W equal to 0 to small w equal to big W. And then we're gonna choose the biggest FW. I'm talking about here. We're gonna choose the biggest one, the maximum FW, as the final optimal value of the problem. And the corresponding PW would be the optimal solution. We're gonna repeat until W equal to W. So every time you're gonna do W equals to W equal to plus 1 until the small w equals to the capital W. And if a small w is infeasible, then we will set it to be NA and never consider it in the future. Let's have a look at one example. Okay, have a look at it here. So I want to solve this knapsack problem. And indeed, you can see this value is not an integer, and it's allowed because it's a value. However, all the weights here, 4, 3, 8, 2, all of them must be integers. And my capital W equals to 12. Okay, initially, I'm going to do the same. Give me 1 second. I'm going to have W first, and then FW. And then I'm going to have PW. But instead of PW, let's make it even more clear. So this is very, very clear. You're going to directly see in each iteration what is the solution. Okay. So initially, let me make it this way. Initially, my small w equal to 0. This gives me a solution 0, 0, 0, 0. And the value is of course 0. What I mean is this. So my I equals to 1, 2, 3, 4. Okay, let me make it a bit smaller. That's going to be more clear. And then V and W. My V's here are 5, 3, 4, and 2.5. 5, 3, 4, and 2.5. And my W here's are 4, 3, 8, and 2. I mean, these numbers 4, 3, 8, and 2. And my capital W here equals to 12. Okay, so these are the data. Now let's have a look. Can I have a combination through all these axes and get the total weight here equals to be 1. The truth is that it's impossible. Why? Because even the smallest weight for x4, the W4 equals to 2. So no matter how you try, it's impossible to make the knapsack weight, total weight, to be 1. So this is not applicable. And then, oops. And once we see NA, later we're gonna do the recursive way, dynamically go back. As long as you see there's something related with weight equal to 1, you just ignore it. It's impossible. We will never count it again. Now let's have a look. Is it possible I can make my total weight to be 2 in the knapsack? Yes, it's possible. Why? Because I can add 1 unit in item 4. See it? And its value equals to what? Its value equals to 2.5. And that's what I'm doing here. I'm doing this step. And then yes, oops. And then yes, from here, my solution will be x1 equal to 0, x2 equal to 0, x3 equals to 0, and x4 equals to 1. And my total value is going to be 2.5. Why? Because this x4 is the most added node. And you go from 0 to 2. Why? Because have a look at the formula, about this formula, see it? And then if you have a look at here, let me make it more clear. If you have a look at here, this calculation, if you strictly do this, you're going to have this one. This is your only item. That's 2 minus wi less than or equal to 2. You have 1 wi less than or equal to 2, which is 0. So that you have this one equal to f0 plus 2.5. f0 is what? f0 is 0. We've already fixed here. So that the value here will be 2.5. And where is it from? In other words, I'm asking which I did you choose here? You choose x4, right? So you're gonna add 1 unit at x4 based on the solution of f0. f0, the solution p0 is 0, 0, 0, 0. So that you're gonna add 1 unit here, and this is a new solution for your W2, okay? And then let's have a look at the W3, what's gonna happen? W3. So using this formulation, you have what? You're going to ask which W's are less than or equal to 3. You find that there are 2 W's less than or equal to 3, which are W2 and W4, right? Okay, use the recursive formula again. This equals to the maximum of here 3 minus 3 equal to 0, then plus VI. Here I equal to 2, VI equals to 3. So the first item is WF0 plus 3. The second item is here, right? Because W4 equals to 2, which is also less than 3. So F3 minus 2, here I equal to 4, okay? What I mean is this. 3 minus W4 equal to 2, so that you're gonna have F1 plus the corresponding value of V4, which is 2.5. You're gonna compare these two. However, remember here, if you go this part, or in the list here, if you go this part, you have what? You have F1 as NA, see it? And as I mentioned, once it is NA, later if you see some calculations with this one, with F1, you will directly delete it. So this is not applicable. You don't consider it. So here, this maximum, you only have one choice, which is F0 plus 3 equals to 3, because F0 equals to 0. So that here, you can say that F3, the value is 0. So how to get a solution? First, copy and paste the solution from F0, which is 0, 0, 0, 0. First, I copy and paste here, 0, 0, 0, 0. And then you're going to ask, okay, where did you go to this new value? Clearly here, I go here from what? From F2, see it? Because why? Because my W2 is equal to 3, which is less than or equal to 3 here. 3 is less than or equal to 3. So that you add 1 unit of your X2 here. And then you go to this value, new value, right? So you're going to add a 1 unit in x2 here, because we come from this 0, 0 solution by adding 1 unit at x2, in which gives you value equal to 3, so that you're going to make f3, the p3 solution to be this one, 0, 1, 0, 0. And now let's have a look at the p4. Oh, sorry, I didn't know if due to the time limit, we're gonna finish this example in the next lecture. So this is all today's lecture. Thank you very much. See you on Wednesday. Bye.